Hello and welcome to the Pendulum Lab Wrap Up. Many of you have done a great job on the Pendulum Labs, and I want to make sure that I kind of give you a summary of the labs that you did so that we can move on with our learning and our understanding. So there were 4 labs, and they were actually quite interesting to me in the fact that the simulation kind of let you just play around with stuff, and although it's not as good as it would be if you were like in the classroom, the simulation worked kind of good. So let's talk about the very first one. I'll go in no particular order, but let's do the mass one. So we're going to change the mass and we're going to see what happens to what's called the period of the pendulum. Now the way this works, the way that you guys set it up is you had your pendulum here, and you're going to pull it back to a certain angle. We'll call this angle, whatever it is, theta. And you pull it back from here. You pull it back and then you let it go, and it comes down here and it swings through here, and then it comes up and back. And if you took the friction off, it would have swung forever. But the time it takes to complete one full swing, so from here all the way back, that time is called the period. And it's a period of time, so we use the capital letter T for period, and we measure it in seconds. And the question was, if you increased the value of the mass that was on the bottom, how would it affect the period? And you guys did a nice job with this. And I don't know if you were like super paying attention or this was kind of novel to you, but you changed the mass here, probably measured in kilograms, and you measured the period here, measured in seconds. And if you're paying close attention, what you would have realized was that regardless of the mass that you put on there, the period never changed. There's no relationship between the mass and the period. This is a weird thing, but it turns out we may have experienced something like this earlier in the year, where if you were to take a bowling ball, for example, and a golf ball, and you drop them, what you realize is that they fall basically next to each other the whole time. They will fall, and they will fall with the same acceleration, and they will hit the ground at the same time. And that's a weird thing, and it's not because gravity is the same for everything. That's a weird statement. The actual Earth pulls more on this one. The force on this one is much, much, much bigger. The force on this one is much, much, much smaller. However, the mass of this one is smaller, and the mass of this one is bigger. So the force-mass ratio is the same for each, which is the acceleration. Same thing applies here. If you increase the mass, the Earth pulls it down more, but it has more mass, so it has more inertia. It's harder to get it to go. And so we end up with this thing going on here, where regardless of the mass you put on, you end up with the same period. You may have experienced this as a little kid. You could get on the swings, and the big kids, the little kids, if the swing is the same, as long as the swing is the same length, they will swing back and forth the same. So that is the mass lab. The next one was a little weird, and I'm going to have to put a little caveat in here for the second one. Oh my God. Just moved my whole board. And the second one, I really wanted you to examine the angle relationship. Now, oftentimes when we're talking about the angle, we use this symbol. It's the Greek letter theta. And in this one, what we wanted you to do was to take your pendulum. So this is where it starts, and then you pull it back maybe this far, and then you pull it back maybe a little farther, right? And you do 5 different angles there. Now, I really should have been more explicit in my suggestion that you do angles like 5, 10, 15, 20, and 25 degrees. Because many of you did like, 15, 30, 45, 60, and 90. If you pull a pendulum all the way up to 90 degrees, it doesn't really behave like a pendulum anymore. So these angles here, they don't really go with these angles here. And so your results may have varied slightly with mine. But if you were diligent and you're paying attention, and you graph this here, again, you're changing the pullback angle, usually measured in degrees, and then over here the period, measured in seconds. Your result should have been another no relationship. Now, how is it possible that if you pull it back farther, it doesn't take more time? Well, you could argue the other way. If I pull it back farther, it's actually going to be going faster. Shouldn't it take less time? And it turns out that these things kind of balance each other out. The farther you pull it back, the longer distance it has to travel. However, the faster it's going down here at the bottom. So if you consider this, right, if we think about just the idea that the speed is equal to the distance divided by the time. This is a general constant. This is the average speed is the distance divided by the time. If I solve for this for time, well, we can have two different situations. If you pull it back a very small angle to start, you have a small distance and a small speed. But if you pull it back farther, you end up with a big distance and a big speed. And small divided by small could be the same as big divided by big. So even though when you pull it back farther, it has farther to go, its average speed is faster, and you end up with no relationship. So that's the first two. Let's look at the next two. In the next one, we were changing the length, and again, we're going to measure the period. So this one I like because, after the first two where nothing really had any effect, all of a sudden we're going to get one, and hopefully it's going to have some sort of effect. And I think you could even just take a piece of string and do the same thing, because if you take a small pendulum or a medium-sized pendulum or a large pendulum, we can see that this one goes back and forth in a short time, this one goes back and forth in a medium time, and this one is going to take much longer to go back and forth. So when you graph this one, you get an interesting result, and this is a result that I need you to pay attention to. So we're measuring the length, probably in meters, and the period in seconds. In this one, you got an interesting result. You probably got some points that looked something like this. Now, many of you assume that this was linear, and you put a linear fit on here, and you got a point over here, and you said, oh, it's linear. That looks good. But I actually don't think that that's true. Okay, I actually don't think that this is a linear relationship at all. Because think about the fact that if this connected right here, what if my period was smaller than this intercept here? That means if the length is 0, it has some period, and that doesn't make any sense at all. The shorter it is, the period should go towards 0. Like 0, 0 should be an actual point here. And so what we have is we have a graph that somehow looks like this. And I ask, what kind of shape do you think that is? That's the real question. What kind of shape is that? Now, it doesn't go up and come back down, because that doesn't make any sense. As the length gets bigger, the period should get bigger. Well, what kind of relationship do you think this is? Well, I would argue one second. I would argue that this is a shape that you are familiar with. This is actually called a square root graph, or a radical, or whatever you want to call it. And what we have here is if I put an actual equation on here using the Desmos, I would say that the period is equal to some coefficient. It's actually, for this case, it's right around 2 times the square root of the length. So this would give you the right shape, and the question is, does it go with your data? It depends, actually. It depends on what you have the gravitational field strength set to. But this is the right relationship, and it's one that I need you to know. So keep this in mind. If you go back and look at your data, one of the things that's cool about the data is that I want to know, if I want to double my time, what has to happen to the length? This is the big deal, right? If I want to double the time, what has to happen to the length? Thing is that I can't just double the length because it's underneath the square root. And if I take the square root of 2, it's not 2. So what would I have to do to the length to get the time to double? That's the question. So this is a question I need you to know. That's going to be a question that you're going to see on homeworks and assessments. What do you have to do? It turns out you have to increase it by a factor of 4, because the square root of 4 is equal to 2. So this idea that you have to increase the length by a factor of 4 because the square root of 4 is 2, that's what you want to do to the time, that makes some sense. What would you have to do to get the period to triple? You'd have to increase the length by a factor of 9. And so this idea here is going to be important for you later. It's a square root relationship between the period and the length. Now, there was one more lab. And this one is purely theoretical because we can't take a field trip to measure the gravitational field strength someplace else. And so this was what they called the gravity. Now, what they're actually talking about here is they're talking about the gravitational field strength unfortunately, they're equating it erroneously with the free fall acceleration. So, and we call both of these, we call them little baby g. They have the same value, they have different units, and they have a different context, but for our purposes, we're just going to call it baby g, they call it gravity. Let's pretend we can change it. We can't change it on Earth, it's always right around 10, but on the Moon it's 1.6, on Mars it's closer to 4. Let's see what happens here. So they allowed you to change it. Okay, they allowed you to change it. So ostensibly, if you went someplace where the gravitational field strength was less, things would fall with less acceleration. They would take more time. They would be slower. So we're going to put the g value down here. They measured it in meters per second. And then here's the period measured in seconds here. So as you increase this, right, As you increase this, the gravitational field strength increases, it pulls things harder, so the time for them to fall should be less. And I think that's what you ended up with. But you ended up with some data points that look like this. And if you connect the dots here, you may get a shape that looks like this. You may be a little bit familiar with this. The problem is, if you put this in Desmos, you realize this is an inverse relationship of some sort. It's inverse because as the gravitational field strength goes up, the period goes down. If you increase the gravitational field strength, the planet would pull harder, which means your pendulum would swing in less time there and back. But if you put this in Desmos and you try to find out an equation for it, what you realize is that it's not inverse square, it's something else. It's actually inverse square root. And so t was equal to, now I don't actually know the number on this one, I should check, hold on. So some coefficient times the square root of 1 over g. This coefficient here depends on the length of the pendulum you are using. So a different length would give you a different coefficient. So what this means here is that as you increase the gravitational field strength, the period actually goes down. Bigger fraction on the bottom means smaller value in general. And so this is the situation you have. And this is a weird situation, but that's what you end up with. So the point that I'm making now is that as you look at these two things, right, the mass didn't matter, the pullback angle didn't matter, the length matters, and the gravitational field strength matters. So how do we take these two things and put them together to form one understanding? That's the real question. All right, I will show you how to do that now. So we have our four variables. We have the mass. We have the pullback angle. We have the length. And we have the gravitational field strength. So mass didn't matter, angle didn't matter, length didn't matter, and gravitational field strength mattered. So if I write the equations that we got here, the generic equation for the period is equal to some coefficient times the square root of the length. This coefficient depends on what gravitational field strength you choose, so different groups may have gotten different coefficient values. For the gravitational field strength, we know it's coefficient, some new coefficient, times the square root of 1 over our gravitational field strength value. So where do we go from here? Well, if this is related to the period and this is related to the period, we know that both of these are related to the period. Can we write one expression that relates all three together? And we can. And we say that the period is equal to some coefficient times, I'm just going to shove them together, L over G. So if you were to keep the G constant, you would have the L relationship. If you were to keep L constant, you would have the G relationship. And this is our situation right here. And so the last thing we need to do is we need to figure out what is the value of our coefficient. Okay? So I'm going to use a capital letter C for coefficient in here. And we're going to see if we can't solve for our coefficient. So the first thing we've got to do to solve for the coefficient here is we got to somehow get it by itself. So I have this here. I can multiply by the reciprocal on this on both sides, and so I end up with T times the square root of G over L is equal to C. Does that make some sense? And so what we're going to do now is we're going to put some numbers in here. Okay? So we're going to use the lab and we're going to put some numbers in here. We're going to use some easy values because why would you not if you could? So I'm going to make my length equal to 1 meter. I know the G value near the surface of the earth is 10 meters per second, or 10 newtons per kilogram, it doesn't matter. And when I measure this, I end up with T is equal to, hold on, I don't want to lie. I'm using the app over here. 1.99 seconds. So, what is our coefficient value then? Well, let's come up here. We know C is equal to the period, which is 1.99 times the square root of, my G value is 10, divided by my length is 1. So, you gotta grab a handy dandy calculator, hold on. So basically, 10 over 1 is 10, I'm going to take the square root of 10. So I end up with 1.99 times 3.16. This is equal to 6.28. Now, if you're paying attention, and you look at this 6.28, does this 6.28 seem vaguely familiar to anyone? When you look at this, now we could do a unit analysis, but I don't want to bore anybody with that. I'm looking at this here, and I'm trying to figure out like, what's happening with this 6.28? Doesn't 6.28 seem familiar to you? Isn't 6.28 2 pi? It is, isn't it? 6.28 because pi is 3.14. This is 6.28. That can't be a coincidence. And so, grand finale, it turns out that if I come back to this one right here, the law for the pendulum says if you want to calculate the period for a pendulum, my C value is 2 pi, and my relationships are square root of L over square root of G. And this is the pendulum law.